13.4. So the first thing we want to do is come up with come up with a couple of definitions. So what are you going to guess? What are we going to guess compound probability means? So thinking of science, when we talk about, in science class, when you talk about a compound, what are you talking about? Multiple things, right? Mixed together. Same idea here. Compound probability is, we're talking about events, we're talking about two or more events. So far with probability we've been talking about one event. Probability of rolling a 12. Probability of picking a blue marble. We want to talk about combining events and how we find the probability of those things. So that's our big question. How do we find probability when we have more than one event? So an example of a compound probability would be draw a 5 and then a king from a deck of cards. So the event, we're doing two separate things. We want to find the probability of that happening all together. And there's a way we can work with the probability of each one to find our probability of our compound event. So there are several different types. We can have independent events. What are we going to guess the independent events are? Now before we answer, think about the marble worksheet that we did after our quiz, where we were drawing marbles from this bag. They had us do we went through this whole process. So thinking about that, what would you guess we mean by an independent event? Go ahead. Resets after we do it? That's a good description. Someone else have another? Okay.
That don't affect the outcome.
Things that don't affect the outcome. Good.
It doesn't rely on what you do.
Doesn't rely on what you do. Did you have something different, Kevin? Say the same thing. Very good definitions of independent events. What independent events means is that the outcome of one doesn't change the other outcome. So one outcome doesn't change the other. Or others, I guess, because we could have more than one. One outcome doesn't change the others. So an example of an independent event would be flipping a coin, getting a heads on a coin and rolling one die and getting a 6. What happens with the coin doesn't change what happens with the die, with the standard number cube. Rolling a 5 on your die and picking a king out of a deck of cards. Whatever happens on the die doesn't affect what happens with the cards. Those are independent events. We also have dependent events. So based on what we just said, what are dependent events going to be? Something that does affect the outcome. One outcome does change the other. So thinking about that worksheet that we did yesterday, what would be an example of dependent events? What do you think? And what happened in the bee bag? Remind us. Every time we drew a marble out, we didn't replace it. So, say we picked a white marble out, there's one less white marble, and there's also one less total in the bag. So that would be an example of dependent events. Picking a white marble changes, and not putting it back, changes the probability for our next pick. So those would be dependent events. So we want to figure out how to calculate these probabilities. Two very easy rules. So let's look at independent events first. I'm going to go backwards. And I'm going to say A and B are independent events. So they're just two things we're interested in. So, for example, flipping a coin and rolling a 6 on a die. The probability of A and B together is the probability of A times the probability of B. And my little rule for remembering, and means multiply. So when we see an and probability of this and that tells us to multiply the probabilities. Find the probability of each one and multiply it. Easy rule. So let's look at an example of calculating the probability of independent events. So let's say we roll a die, a standard number cube. One die. And draw from the 4 letters A, B, C, D. We want the probability of rolling greater than 3 and B. So we roll the die, we pick a number, we want to find the probability that we get a number greater than 3 and a B. Did the die, rolling the die affect picking the number? Does it change it? No? Question?
Would you mean getting like C or D or just the letter B?
Just B. So we pick in and draw one letter out. We want the probability that we roll a die, we reach in one, pick one letter out, the die shows us more than 3, and we have a B. Okay? So these are independent. It's an and probability, 3 and B. So this tells us to multiply. So let's calculate each of the individual probabilities. Probability, I'm going to write this as greater than 3. How many numbers on our standard number cube are greater than 3? 3. 4, 5, and 6, right? So probability is 3 out of 6. We have 6 sides on our die. Is 1/2. What's the probability of picking a B out of those letters? 1 out of 4. So our rule tells us, this is an and probability, tells us to multiply. So the probability of greater than 3 and B equals 1/2 times 1/4. And when I multiply fractions, how do I multiply them? Straight across. Multiply straight across. So 1 times 1 is 1. 2 times 4 is 8. So the probability of rolling greater than 3 and a B is 1 in 8. Pretty easy rule. Questions there? Okay. Let's look at an example with a dependent event. So this will be like we'll calculate a probability like we did, just like we did on our worksheet. So let's say we have our jar. With 5 red and 6 blue marbles. We're going to draw a marble without replacement. So that's one way that they'll tell you don't put it back. Draw without replacement. We want the probability of blue, then red. We could also think of this. We're doing two draws. We could think of this as the probability of, I'm going to write it this way, blue and red. So I'm going to just make a note over here. We're going to do two draws. Blue then red is the same as saying blue and red, because we're going to draw one, then we're going to draw the other. And tells us to do what? Multiply. So let's calculate the probability of blue. And after we pick the blue, they're dependent events, we have to calculate the probability after we pick that blue. So on our first draw, we want to pick a blue. Yes? I'm sorry? No, then is the same as and. Because we're picking twice. So we're picking a blue, and we're picking a red. We could say blue and then pick red. So then and are the same. It tells us to multiply, so this is the same as and. All right, so what's the probability on our first pick? What's the probability of picking a blue? 6 out of 11. And then after we pick that blue on our second pick, so this is first pick. On our second pick, what's the probability of picking a red? 5 out of 10. Because I don't put that marble back, I have a total of 10. So that's why we call them dependent events. The probability of this one depends on the probability of that one. And then we're going to calculate together. So the probability of blue and red equals 6 out of 11 times the 5/10 equals 1/2. That's 1/2. So I get 6 out of 22. Can I reduce that? 3 over 11. Very nice. Divide everything by 2. 3 over 11. So our chances are about 3 out of 11 of picking, our theoretical probability is 3 out of 11 of picking a blue then a red. Yes?
So it's like, it makes me think of the person who has to like minus what you take out.
Right, exactly. So before we calculate the second probability, we have to think about what we took out of it, and then we do the exact same thing. So the way you described it was perfect. Are we good with this one? Not too difficult. It's really the same thing as the last one. We just have to calculate our second probability after we've done this first pick. All right. So the the last kind of probability we want to talk about, we have one more special kind of event, or events for compound probability, mutually exclusive. What are we going to guess mutually exclusive mean? What does mutual mean? Together. And exclusive? We're excluding, right? Mutually exclusive means they cannot happen together. We're excluding them happening together. So Romeo and Juliet, were they mutually exclusive events? Kind of,
They
sort of.
ended up together.
They ended up together, right? So the theoretical probability is different than the
Cannot, but they did.
they cannot, but they did. Different than the experimental probability, right? So if we're talking about events that cannot happen together, what would the probability of A and B, if they're mutually exclusive events, what would the probability, how would we write the probability of A and B? They can't happen together. What's the probability of something that can't happen?
What does it mean by they
They cannot. It's impossible. Like flipping a heads and a tails in one flip of the coin. No, they can never happen. So a heads and a tails on one flip of a coin.
Isn't that understood though? If you pull one, you can't pull an A and a B.
Right, right. So those are mutually exclusive. So what would be the probability? Impossible, and we write that as a 0. So probability of mutually exclusive events are 0.
I like these problems.
You like these? Where it's just 0? All right. But we can figure out the probability of A or B, right? One or the other could happen. The probability of A or B for mutually exclusive events, they can't happen together. So we want to see one or the other happen. We have another simple rule. Probability of A plus the probability of B. So or means add. So mutually exclusive events can't happen together, but one or the other can happen. We could flip a heads or a tail. We could draw an A or a B. When we get that kind of probability, we add. So we just have two rules: multiply or add. And means multiply, or means add. So let's do an example of mutually exclusive events and finding an or probability. So we have our jar, and it has our marbles. We haven't lost all of them yet. 3 red, 4 blue, and 5 green. We want to draw once. And we want the probability of red or green. The probability of red or green. Or tells us to add. So what's the probability of red on one pick? 3 out of 12. And let's leave it, we won't reduce it yet. Probability of green on one pick? 5 out of 12. So the probability of red or green is 3 out of 12. Plus, or means add, 5 out of 12. And we add those together and we get 8 out of 12, and we reduce that to 2/3.
No, guys. And then 3 plus 5 plus 2/3.
After one step, we get 2/3. So that's why we didn't reduce the fraction here, is because we knew we had to add, and that we'll have a common denominator. The 12 will be our common denominator. Our total will be our common denominator. So there's our 2 rules. And tells us to multiply, or tells us to add. And if we have dependent events, we just have to, our second probability, we have to calculate it after the first one happens. Questions? Okay. Homework? And I'll pass back the folders and we'll go over our worksheet. So hopefully the and the or probabilities should be pretty straightforward.